Yeah, before I want to introduce the PFC, the predictive functional control, I want to tell you two main disadvantages of my special version of a deadbeat controller. Two disadvantages. One disadvantage is the control difference in disturbance behavior. Control difference in disturbance behavior. This I have shown. So there will be a control difference if there is a disturbance in front of the process. My special version of the deadbeat controller, the DB BY, cannot compensate completely the disturbance. That's the first disadvantage. I have a solution for this. See solution in chapter 9. I have to look. 930. Yeah, this is solved and not so big, but there is a second big difference. High noise gain if T0 is small. So what we can say is the controller will be very fast depending on the sampling time. The faster the sampling time is small, but the smaller the sampling time, the larger is the noise gain. To show you this, note deadbeat controller for our 2PT1 process we have used in an experiment just before, where the K is 0.4. The one time constant is 0.1 second. The second time constant is 0.2 second. We have done the experiment with sampling time 10 millisecond. Yes, I have reloaded this controller. 0.4, 20 millisecond, 100 millisecond, 10 millisecond sampling time. If we click on the deadbeat controller, we see the Q0. That is a dominant gain factor is 67, around about 67. So we noted Q0 is 67. That means 1 volt step caused a 67 volt step at output. So if I have 1 millivolt noise is just a signal which could change very fast, then this noise is a 67 millivolt noise at the output. Doesn't matter, but the question is what happens if I now decrease the sampling time, and I want to show you what happens. And my deadbeat control version has the same gain, because without limitation is as fast as the deadbeat controller. So we can say the Q0 of a deadbeat controller is a very good measure instrument to check the gain of my version of deadbeat controller. So change of sampling time to half of the value, to 5 millisecond, leads to the following result. I reopen the design window. Now I change the sampling time to 5 seconds, click on controller design again, and then you see the Q0 now goes dramatically in the in the high. So we have here a 232 value. 232 value. 232. So a 1 millivolt noise is gained with 232 gain factor to 230 millivolts, and then you see this very high noise on the actuator output. And noise on the actuator output could produce very big loss of power of energy or heating of actuator and motor and so on. So if you want to have small time constants, this gain leads to a high load of your actuator. A short demonstration should show you what I mean. Yeah, I open the adaptive controller. I have set the hardware simulator exactly to this value. I go back to the controller design window and rechange to 10 milliseconds. That's our original controller. Send this controller to my control loop. Hardware simulator is just set. Then I can show you the comparison of a PID controller with unit step function, reference step response. You see this is the response of my PID controller, and the PFC controller can also be set. All things are well. I want to have H1. I recalculate the A's and B's and say run, advanced view, select PFC controller, start. You see, in this case, now the PFC is a little bit faster, no overshoot, as fast as possible, looks very good. Now I delete these curves, go back to PID and make a change. In my hardware simulator I have the possibility to add a noise, a random noise signal produced with the internal random generator of the C# software. That means the output of the process now gets a noise of 50 plus to minus 50 millivolt maximum. That is the amplitude, and the noise is between 0 and 50 millivolts. So in middle 25 millivolt noise in both directions. If I run the system, you see this change, this noise here on my X value. And now I show you the reference step response of both controllers. You see, I have to shift this a little bit that you can see the time axis. The noise happens as a small change in the actual value. If I change the controller to my version, then this looks very similar. So you think, okay, both controllers behaves very identical in this case. But now I show you the controller output, so the actuator load. What has the actuator to do? If I click on the actuator output value first, delete both curves, run in a process, look what happens with the PID output. You see first the impulse to get the final value, and then here small change around 2.5 volt. 2.5 volt DC value is necessary with a gain 0.4 to get a 1. So yeah, the average must be 2.45 volt. That looks good. Small change, plus to minus a little bit around half a volt. And now look what happens with my version of controller. The process output looks very similar, but if we look for the noise signal on my actuator output, you see a very large changing. Here you see plus 10 volt to minus 10 volt to minus 7 volt. So this is a much higher amplitude as we want to have it, because this is really heating of a motor. If we have a DC control, you will see this in the lab. Yeah, and if you feel, put your fingers on the motor after some minutes of controlling, in this case, you see a very hot motor. More dramatical situation we get if we divide the sampling time by 2 to go to 5 milliseconds. Let's check. First the design, 5 milliseconds. Controller design, sent to the controller box. Then we need the hardware simulator. The hardware simulator also has to be changed to 5 milliseconds. We have new A's and B's, same noise. And finally the controller output values. I delete these curves and run again. Init process, first PIDT1. You see here the noise on the actuator output is larger, nearly by a factor of 2. Okay, but now see what happens. The Q factor are 4 times larger, so the noise gain is 4 times larger than before. And if I show you these curves, then you will see this doesn't work. So we have just a change between plus and minus maximum value. Yeah, this is a really a strange behavior, in spite of the fact that the controlled value looks not bad. Sorry, I want now to have process output, run init process. Yeah, this looks good, but behind this effect, we hear the noise. Yeah, if you have a real hardware system on the table, this plus to minus maximum value means full power, full brake. It's really a hard load for the system. So this is a big disadvantage of the deadbeat controller solution, independent if this is the original one or my special one. So we need a different design, and this comes now with my presentation of the PFC, the predicted functional control, called this controller. The inventor, the developer of this controller, is a French scientist, rather old. I've seen him 7 years ago, and then he was 80 years old. I'm not sure if he still is alive, but he makes workshops also in this age to sell his new design. Okay, look into the theory. So in our example, we go back to a PT1 process. Go back to simple PT1 process to come slowly to the theory. In the simple PT1 process used in previous examples, we have the same K, but it's time constant T1 from 1 second, and we have worked with 100 millisecond sampling time. Assume that there are reasons to have a much smaller sampling time. Here, in this case, yeah, to show the DBC, that B controller has a Q0 of 26.3. Is that what we have done in this previous example? Now reduce sampling time to 1 millisecond. To 1 millisecond. And you want to have a good controller. Note that in this case, at DBC, you can calculate it with my tools, now has a changed Q0, which is 2500. We have a noise gain of 2500 and 1 millivolt noise gets a 2.5 volt noise on your actuator output. That is absolutely not acceptable. Forget it. Yeah? A deadbeat controller with small sampling times is not usable. And now, for this purpose, a predictive functional control can do the job very good. The idea is described in the beginning of the chapter 975. The Richalet PFC is described with this picture. We have three signals: the desired value, the output of the controller, y of k, which is the goal to calculate it. Yeah, don't forget, in each step we want to have a new y of k value out of our algorithm. And x is the assumed process output. So here I can look for the control difference. That are the blue arrows here. The control difference here is xd for the time point k, the actual time point. Then one step in the future I want to have a new control difference which should be smaller. And now the difference to a deadbeat controller is I now want to look a free number of steps into the future. The number of steps I look into the future is h. It could be 2 or 10 or 100, so it doesn't matter. This design, this controller, in opposite to a deadbeat controller, don't want to be ready after 2 steps. In this second order system, it could be any number of steps. So that is the difference. We are using our model prediction to look more than 2 or 3 or 4 steps into the future. That is a free choice of numbers, so we can look 100 steps into the future or more. Yes, and the next step is the resulting closed loop curve. That is the closed loop response of my closed loop system. Is a red curve. The control difference should be smaller from step to step. You see, the lambda here is a reduction ratio between the new control difference and the previous control difference. And if I say, okay, the decreasing factor, the reduction ratio, should be constant. And I call this lambda index r for reduction. So from step 1 to step 0, I reduce the control difference by lambda. From step 2 to 1, I also want to reduce the control difference by lambda. So in 2 steps, the reduction is lambda squared. If I'm more than 2 steps, 3 steps, I have lambda to the power of 3 and so on. If I have h steps, then I know after h steps, the reduction ratio is lambda r to the power of h. So this is the first assumption of theory. Note that the number of steps, which I look into the future, the author called horizon. I look into the future and see a horizon, which is h steps of my sampling time. H is free choice. In the PT1 process, the author recommend just the age of 1. I have to look only 1 step into the future. In higher order systems, so PT2 or IT1, there is the possibility and opportunity to select an age which is much higher than 1. So we can really look many steps into the future and then get better control behavior. So the next step is now an idea. The author introduced now 5% settling time. Yeah, it's rather free choice, but other things or his experience is a 5% settling time of a closed loop system is a good measure indication, and the user can select in this design, can select this 5% settling time. If we investigate this 5% settling time in a very simple system where the closed loop behavior behaves similar to a PT1, look, the PT1 step response is a well-known function. H of t is the unit step response. H of t is 1 minus e to the power of minus time divided by the time constant of the closed loop process. Then we know after 3 time constants, that is the thumb rule, yeah? After 3 time constants, this exponential factor is 0.95. So e to the power of minus 3 is 0.95. And that means the 3 times process time constant is the 5% settling time. Yeah? So we set the settling time to Tc, and now in a PT1 process, the time constant of the process is 3 times larger. That's the first idea. And now look into the I make a new picture. Look into the step response of this PT1, and then we check how we can come to a lambda factor. To understand this, we just draw the closed loop behavior. So this is x of my system. This is the desired value, say WO. And this is the starting value. We can do this with 0. So then we have time constant of the closed system, closed loop system. This was the t, and we have the 5% time Tc. Yeah? If this is smaller 5%, then we know this is Tc, and if this is a time constant of the process, we know this is 3 times the sampling time. Okay, now look for the control difference. Now the first difference is of course the complete so the control difference at K0 is W0. Now we sample here at 1 sampling time, so K is 1. We have a K plus 1 value. If this is K, this is K plus 1. If we start with, let's call this K. Oh, sorry. In my paper, this is K. Any position. If we have the next step, what happens with the control difference? This was marked in blue. How large is this value? If the black curve has the behavior 1 minus e to the power of minus t over t, that is the x output, then we know the control difference of the system is the difference between desired value and actual value. And if we put this equation, both equations together, then we get omega W0 minus W0 times 1 plus W0 times e to the power of minus t over process time constant. That is the xd value. The first xd at position k is w. Let's look what happens at k plus 1. One step further. At 1 sampling time, we have then the control difference. You see this value can be eliminated, is w times e to the power of minus sampling time divided by process time constant of the closed loop system. xd of k plus 2 is wo times e to the power of minus sampling time divided by time constant, and the sampling time is now multiplied with 2. and if we write it in a different way, then we can say, like the paper, this is xd of k. xd of k is w, warte mal, sorry, xd of k times e to the power of minus sampling time divided by t, and xd of k plus 2 is, if you see this, is xd of k plus 1, the previous signal multiplied with the same factor. And you see, really, this factor is my used lambda. The reduction factor from step to step is e to the power of minus sampling time divided by t, and with our desired settling time of 5%, this tc is 3t. I replace now the unknown time constant of the closed system with my desired 5% settling time. So I get the important expression in PFC control system. Lambda index r is e to the power of minus, if I solve to t, t is tc divided by 3, then I have 3 sampling time divided by tc. So this can be calculated in the beginning of the design of the controller. So these are user parameter, user selection, T0 and Tc leads to a given lambda factor. Example, I want to have in our process with my 1 millisecond sampling time, I want to have a Tc of 500 millisecond. That is okay for me. 500 millisecond. Yeah, the user said, okay, half a second is a good 5% settling time. This leads at once to a lambda factor. Lambda r, it is a number example, is e to the power of minus 3 times 1 millisecond divided by 500 millisecond. That means in the digits this is 0.9940. Okay, so we know that in each step I want to reach the final value within 5% in 500 milliseconds. There are 500 steps. If I do this 500 times, then I should be within a 5% tolerance range. Check it. Yeah. Check. Do this reduction. 500 times. What happens? I have to take my lambda to the power of 500, and with my calculator I calculate then 0.994 times 500, and this gives this gives 0.0478. Stop. 0.0493. This is less than our 5%. That's good. Now, if I say, okay, I want to look 10 steps into the future or 50 steps into the future, what happens now? Now, look with age is 50 steps into the future. Then we see after 50 steps the lambda lambda r to the power of 50 then will be 0.7408. What does that mean? That does mean that now I'm 1/10 of my 500 millisecond, and I know after 50 steps the reduction must be 0.74. This is to 25%. Then the next 50 steps I again decrease with the factor of 0.74. This I will do 10 times. So finally, after 10 times of this 50 steps into the future, this 0.7408 to the power of 10, I again, if I do this, let's calculate this with my calculator. This again gives 0.0498 value, which is smaller than 5%. Yeah, so independent of the looking into the future in our PT1 system, I always need 500 steps to have 5%, and I know now my reduction factor, which is 0.994, which is calculated with given values. That is the first step of the theory. Now we have to find a way. Now calculate y of k. Now that is the next idea. Note that this theory assumes that during my prediction of 50 steps, I assume that y of k is constant. That is different, a difference to my version of dead beat. I predict one y of k, then I predict a second y of k plus 1, and the third y of k plus 2, and so on. So they are all different, and I calculate with these different y values the response. Mr. Richalet assumes a constant y of k, but this is of course not constant in my controller. In my controller, in each step, of course, I calculate a new y of k. But I look 50 steps or 100 steps into the future with the assumption that in these steps y of k is constant. That is the basic conditions of this controller. Okay, next steps. Here you see in my paper, note that I have made some changes. Please download version 3.4 because I've just modified this chapter a little bit, optimized this a little bit, so that this fits to my my calculations here. Here you see the same examples, and we will see this later in a simulation. Now the next step comes. Now with our PT1 process model, we look deeper into the predictions. Yeah, we assume that the process is a PT1, and we have a PT1 model with given A and B. So we have just to repeat this a little bit and work a little bit deeper into the next point of theory.